Uh, J.P. Ryder told me to do this, and it sounded like a good idea. I'm not a very good speaker, but these are the explanations, the verbal explanations of my diagrams that I've always posted online. I'll just get straight to the point. Um, the top image is a recreation of a diagram that someone sent me on how they thought that you could make something invisible by having 3D pixels that line the surface of an object. This is just a cross section, and light would go through the object and go out the other side, but they didn't know how to send light through. My solution is the interface. The interface, this is a cross section again, and it takes the same shape as the object that's being made invisible. It only shows the fiber optic cables or bundles that where the light is coming through at. I didn't have enough time or the patience to draw the other fiber optic bundles connecting the outer 3D pixels to the counterparts on the interface. The interface is a small concentrated volume of the same shape that the object is resting in space, and it sends the light through as if nothing's blocking its way in a concentrated volume to where you can fit other things inside the craft or whatever you have, a battle suit or whatever. But the light, and I'm not very good at pointing with this, I've never done this before, the light goes through, and it goes through the fiber optic, goes through the hollow interface, which is nothing but an optical screen structure, and it goes back out the fiber optic cable, and it goes back out along its way as if nothing's impeding it, and it allows for other things to be put inside the aircraft or the spacecraft or whatever. But this is a cross-sectional view of the solution to this guy's idea of how to send light to an object. He got the three-dimensional pixels right. He just needed to apply concentrated volume. That's the philosophy behind the interface. It's the concentrated volume that the object is resting in space, and you just connect the outer surface to the inner surface of the surface of the interface three-dimensionally, and it sends light through as if nothing's impeding its path. Okay, now switch to the other one. This second diagram is a three-dimensional perspective of the interface. This is the ship, the same ship you saw in the first one, but that was a cross section. This is a three-dimensional representation, and this is the interface. Some of the paint's been eaten away off this transparency, but this is the interface, and these are the fiber optic cables connecting the three-dimensional picture elements of the surface of the interface to the three-dimensional picture elements on the surface of the ship, and that's all that is. The interfaces will take the same shape as the object that's being made invisible, but in a smaller, more concentrated form. The interface solves the problem of making things invisible with moving parts like this battle suit. The interface is a puppet interface, and it's rigged to the arms and legs, the appendages of the suit, and it's made to move in time with it. All the while it's connected through fiber optic bundles again to its counterpart on the interface, and it sends light through as if it wasn't there. If it was hardwired, you'd have to change the hardwiring every time the suit moved, even an inch or whatever. But with my interface, and I'll show you in a second why my interface is important for a number of things. This is the typical idea that people have of sending light to an object. They want to hook up one three-dimensional picture element to every single other one, and you can imagine the web it would create if every single three-dimensional picture element was hooked up to every other one with single fiber optic wires. Light comes in, goes through here, comes out here, and that's almost impossible to do. I mean, it's a really complex idea. It's more complex than my idea of the interface that solves that problem. My idea is an interface. Again, it takes the same shape as the object being made invisible, but in a smaller, more concentrated form. This is another cross section. Cross sections are a good way of studying the webs of light that's being made through the interface. This is the interface, this is the outer object. Light goes through the fiber optic bundle, through the three-dimensional picture element, through the fiber optic bundle, connects with its counterpart, three-dimensional picture element, and is sent through, going straight through to the fiber optic bundle on the other side, through the picture element on the interface, to the fiber optic bundle on the other side, to the receiving three-dimensional picture element on the outer surface. Light goes through and takes the same path that it would take if the object wasn't there. This is sort of misleading. This light don't go in and spread all the way through to the other ones, but it shows what would happen if light was coming in every direction. It would spread it. It would reproduce the web that the wires would make if it was hardwired. But the web is a floating web of light inside the interface. It's a disconnection. It's a floating disconnection, or I don't know. It's what allows the appendages of a moving battlesuit to move, because it's not hardwired per se. It's connected through fiber optic bundles, a one-to-one correspondence. A one-to-one correspondence. The previous diagram was a one-to-many, where one three-dimensional picture element was hooked up to all the others by single fiber optic strands. This idea, the one-to-one correspondence that my interface is all about, it has a bundle instead of a single wire of fiber optics, and it hooks from the outer three-dimensional picture element to the inner three-dimensional picture element in a one-to-one correspondence. And that solves that problem. This is an image of an object, a spherical object, the cross section, and even though the three-dimensional picture elements are bigger, it just makes drawing the web simpler. If you put thousands of them around here, it'd take forever to do. So I usually draw the three-dimensional picture elements bigger and make everything more simpler. But this is the web that would be created if every single picture element on the outside was hooked to every single picture element on the inside. To their corresponding three-dimensional picture element, one-to-one correspondence, by way of fiber optic bundles, and it would be sent through and out their direction in the same path that they came in, and it would create a web like this. If all of them were active, that's the web that would be created. And there's different other types of webs that you can visualize through different other shape objects, cross-sectional shapes that you can visualize. But a sphere has the highest form of three-dimensional invisibility resolution because light travels through it at regular intervals. Any other shaped object, like a square or a triangle or complex shapes, there would be less three-dimensional resolution. By now I'm sure you know that the interface can also act as a holodeck, a type of visual holodeck within the invisible sphere. If somebody were inside it, they would see light coming through in all directions at all angles, painting a three-dimensional mural all over the walls of the interface as if they were out in the environment that the light is coming through at. You don't really need this outer layer. That's really for invisibility. You could have just a single sphere like this with three-dimensional picture elements all around it, and light would be received and sent through. You can record an image of an environment, or you can have a computer program to make a three-dimensional environment. But this is workings of a holodeck. And a holodeck is inversely related to invisibility. You turn one inside out, you have the other. Outside it's invisible if this person wasn't in here. Inside it's a holodeck because you're right in the intersection of the light going through that certain point in space. I'm only going to touch on these because these are a little bit too hard to explain. This is the second property of the holodeck, the interior of the holodeck. If you had the interior of each holodeck hooked to each other and also hooked to the outer surface that brings the outer light in to illuminate the interior, if one person was standing in a single holodeck, another person was standing in another corresponding holodeck connected to each other through these inner wires or bundles, then the result would be two holodeck images of two people or furniture or any other object within a recording interior meeting up with each other. In a real holodeck, two people wouldn't walk in like on the Starship Enterprise. It would be one person to one single chamber, and the result would be that they would meet in the third chamber. Only their holograms would meet. Okay, briefly touched on that. This is an idea of an artificial parallel reality. You have, do I have that backwards? Yeah, I do. You have a interface that connects to all the three-dimensional pictures around the sphere, and it sends light through. But you have another interface that acts solely as a holodeck, and it's hooked to a computer program or a recorded environment that plays in here. So this is the workings of an artificial parallel reality. You need to be invisible to the outside world, and you also got to experience your own reality inside, and you'll be totally cut off from this world, and you'll be experiencing another reality. This is a theoretical, virtual, artificial parallel reality. There's a paradox of mine that I call the ghost interfacing, the paradox of ghost interfacing, and it's a little bit more advanced than the stuff I'm trying to explain now. But imagine if two invisible, completely perfect invisible objects, not only to light but to matter, were to meet up to each other. Would they feel each other in our reality? I'm not even going to go into this too long. This is how you take pictures. This is moving on to the lenticular box, the low-tech proof of my theories in invisibility and holodeck technology. You imagine a box in front of you, and you take pictures on both sides of an edge to assemble those pictures together in louver form up and down to create an image, a larger image from two sides. And then you go around the box and you take flat straight-on pictures of the flat straight-on part, and you do this to all the sides and all the flat panels of the box, and that's how you create a lenticular box. The lenticular box, this shows the inverse relationship on a low-tech level between low-tech invisibility and low-tech holodeck. On the outside, you have a series of louvers on one edge, one panel, adjacent to another of the same colored louvers, and they represent a full larger image at that angle. And so at this angle, yellow louvers, and so at this angle, brown louvers, and they create full images, and you still have the straight-on images behind them, flat straight-on images. The way to convert this outer lenticular box to an interior holodeck lenticular box, the way to convert an outer invisible box, low-tech invisible lenticular box to an interior low-tech holodeck box, you take this panel and you push it through to where it's straight facing the way it was, but it's on the opposite side of the box. You take this panel and you push it straight back through to where it's facing the same way it was, but on the opposite side of the box. You take this panel and you push it straight down to where it's facing the same way it was, but to where it's on the opposite side of the box. And again, you see the louvers line up, but you're supposed to switch each louver to their counterpart, and switch the browns with the browns, switch the reds with the reds, and that's how you invert from a lenticular low-tech invisible box to an interior low-tech holodeck box. And this is the low-tech proof of my theories of invisibility and holodeck technology being inversely related to each other, or invisibility and holography being inverse. And this is just an idea of what it would look like inside of a lenticular box if you had it large enough in holodeck mode. As you go around the angles, the images would change and would be more faithful to the perspective in a real environment than just flat murals painted on a wall. And this is a picture of a beach with somebody inside and everything. These are just pictures of the old Smothers Park. This is my lenticular box at an edge, and this is where two images come together to create one larger image at that angle. This is the actual lenticular box that I built based on my theories and diagrams and everything, where I figured out. And there's three axes that you notice in the other one. One is the straight on axis that goes all the way around the box. Another one goes at one angle of the box, or one other axis of the box. Another one goes around the other axis. There are three axes around the box. It takes 30 pictures to create one lenticular box, and you get 18 viewing angles as a result, because two pictures at an edge-on view create one angle of view. So from 30 pictures, you're reduced down to 18 viewing angles, because you have flat surfaces and you have edge-on views. And this is a picture looking out towards the bridge at the old Smothers Park. This is a picture. Oh shoot! This is a picture looking down at the river park, and the office across from it, the office house, and the parking garage or whatever. And there's my mom's car, by the way. She's waiting for me to take all these pictures. And this is an edge-on view again. I'm going around in angles, or in whatever. This is a view looking towards the American Legion at the old park. That's the American Legion. This is the sidewalk over here. It's going to be the gazebo. And this is the final angle on the lenticular box. I'm only showing angles, not panels. But here's a tree that used to overlook Smothers Park, overlooking the river. And over here, just barely out of sight, is the gazebo, the old gazebo. And this is the old park. And I didn't exactly get the pictures matched up correctly. But, you know, it's an art and a science, I guess. I don't know. And that's the last image of the lenticular box. This is the origami of the lenticular box. This shows how you can also, the first lenticular box I made, I folded it from a flat surface with cut out areas into a panel, and then I added 6 panels together to create a lenticular box. You fold at the creases that are marked here, and it's color coordinated, or color coded, and when you fold them, the browns become the browns facing your direction, the red are the flat panels, the greens folded facing your direction, and these are other colors that are hidden from you in this perspective of a folded panel. And this is the last one. This is a further progression of the origami of the lenticular box. And Jesus, this paint's coming off here. But this is an unfolded lenticular box. It's just 6 panels, the same panel you've seen in the other one, but there's 6 of them connected together, and there's cuts cut in at the corners in some places to allow them to bend. So when everything's folded down, you get a lenticular box, a folded lenticular box, and it's decreasing size, but the pinks are facing each other and creating a angle view. The greens are facing the yellows are facing each other, creating an angle view, and the pinks are folded and facing each other towards that direction, creating an angle view that way. There's 3 different axes around the box. Well, I guess that's about it. I hope I've explained enough for you, and like I said, I'm not very good of a speaker, and this is an experiment. So, well, I hope you've understood a little bit more than what you can do with just looking at my posts. Well, I guess that's it.